Hello everyone, welcome to the series of lectures on the course Foundations of Mathematics. In this video, I'll be talking about intersection of family of sets. In the last video, we have already seen the notion of family of sets and we already discussed the union of families of sets, right? So now let's see what is intersection of family of sets. So the definition goes this way. If I have a family of sets, a collection F alpha, where alpha is coming from delta. So supposing I have a family, which is this. So let this be a family of sets indexed by the non-empty set delta. So this delta is the indexing set which I am talking about here. Supposing U is the universal set, then we define the intersection of family of sets by this. Intersection of all F alphas where alpha is varying over the indexing set delta. This is defined to be the set of all elements X in the universal set such that this element X is present in each and every alpha, right? So this is nothing but the set of all X in U such that for every K in delta, no matter what point K in delta you take, X will be there in that Fk. So this element X should be there in each and every Fk, where K is varying over the indexing set delta, right? Then only the point X is going to come in the intersection. It should be there in all of them. Now that is same as saying intersection of F alphas where alpha is varying over the indexing set delta is the set of all the elements in U which belong to all the F alphas, right? So same thing it is, just worded in a different way. Now we have one comparison between the intersection of a family of sets and union of the same family of sets, and that relation is this. If I take a family F alpha with the indexing set delta, then intersection of all the F alphas is a subset of union of all the F alphas where alpha is varying over the indexing set delta, right? So intersection is always a subset of the union, provided these sets F alpha they are from the same family. So let's try to prove this. I want to show that this intersection of all the F alphas is a subset of union of all the F alphas. So let me start with the point in the intersection of all the F alphas. So let X belong to intersection of all the F alphas where alpha is varying over the indexing set delta. Now because X is there in intersection of all the alphas, X will be present in each and every alpha, right? So that thing is clear from here. Now we know that we will make use of the fact that the indexing set delta is non-empty. I will make use of this fact. So since the indexing set delta is non-empty, I can pick up at least one element in this delta. So there exists a, a point beta in delta. Now X is there in F alpha for every alpha in delta. In particular, this beta is also there in delta, right? Therefore, the point X is going to come in F beta also because it is coming in all the F alphas where alpha is in delta, and in particular beta is in delta, so X must be coming in F beta. So X is coming in at least one of the F betas, right? So this implies X is there in all of them because it is there in at least one of them. Sorry, pause. So this implies X is there in union of all the f alphas where alpha is coming from the indexing set, because it is there in one of the f betas. That means we have shown that intersection of all the f alphas is a subset of union of all the f alphas where alpha is varying over the indexing set delta, right? So intersection of a family of sets is a subset of union of the same family. So let's look at few examples now. Yeah, look at this example number 1. Consider the family of sets defined by fk, and it is defined to be the set containing 0, this k, and its negative minus k, where k is varying over the set of all natural numbers. So let's compute few sets of this family and see how it looks. So when k is equal to 1, I will get a set of this form: -1, 0, 1. When k is equal to 2, I will get a set of this form: -2, 0, 2, right? And in this way, when k is equal to, let's say, 123, I will be getting a set of the form -123, 0, and 123. So if I put it on the number line, how will it look? So 0 is here, 0 is there. In f1, the point 1 and -1 are there, along with 0. 0 is there in all of them. In f2, the point 2 is there, -2 is there, and the point 0 is there. In f3, 3 is there, -3 is there, and 0 is there. So when I take intersection of all of them, which points are going to come in the intersection? That means I have to find out which points will be coming in each fk where k is varying over the set of natural numbers, right? So from this, it's quite clear that it is only the point 0 that is coming in all the fk's. So our claim is intersection of all the fk's where k is varying over the set of natural numbers is the singleton set having the 0 element. This is what we have to prove. Okay, so we will prove that these two sets are subsets of each other. So by the definition of fk, it is quite clear that 0 is coming in each fk for each k in n, right? So since 0 belongs to fk for all natural numbers k, right? So therefore 0 is there in intersection of all of them. Because it is there in all fk's, for each k it will be coming in intersection of all the fk's, right? So it is there in intersection of all the fk's where k is varying over the set of natural numbers. So this point 0 is there in intersection of all the fk's. So from this I can say that the singleton set 0 is a subset of intersection of all the fk's where k is varying over the set of natural numbers, because every 0 is the only point here and it is there in the intersection of all the fk's. That means this singleton set having 0 as the element is the subset of this intersection of all the fk's. Clear? So one side I have already proved, and I will name this as 1, Roman number 1. So now we have to look at the other side. Now what I have to do is, we have to show that intersection of all the fk's when I take, that is a subset of singleton 0. That means any point if I take here in intersection of all the fk's, then it will be present in this set. That means that point is going to be 0 point, right? So we will do this using contrapositive. We have already studied the concept of contrapositives in our first chapter. So to prove this, what I have to show, if I take a point x in the intersection, then x must be present in this set. That means x must be 0. Its contrapositive will be if I take a point which is not there in this set. That means I am taking a point which is non-zero. Then that point will not come in this intersection, right? So I have to start with a point which is not there in the singleton set 0. So let me start with a point. Supposing a point x does not belong to the singleton set 0. Because it is not there in the singleton set 0, I can conclude that x is a non-zero element, right? X is some non-zero element. Now, because our universal set here is the set of integers, this k will be a non-zero integer. Okay, so k is a non-zero integer, so it could be positive or negative. So to make sure that this I get a natural number from this point x which is non-zero, what I do is I take its absolute value. Okay, I take its absolute value and you just add 1 to that. And you consider this as some number, let's say MC. Then because x is an integer, this x will be a positive integer now, right? It's a natural number and I'm adding 1 to a natural number. So the number m will also be a natural number. So I found a natural number m which is modulus of this k plus 1, right? So the point x is not going to come in this fm, because what will be fm? It will be mod x minus of this 0 and mod x plus 1, right? And this is a non-negative quantity and I'm adding 1 to it and subtracting 1 from it in both the cases. So this can never be equal to x, no matter what value of x you pick up non-zero. That means we have found one natural number m such that x is not there in fm, and if it is not there in at least one of the fm's, this implies it cannot come in the intersection. That means x is not there in the intersection of all the fk's where k is varying over delta, not delta, the set of natural numbers. So if I take a point which is not there in singleton 0 set here, then that point cannot come in the intersection of all the fk's. Okay, so by the concept of contrapositives, we can say that intersection of all the fk's where k is varying over the set of natural numbers is a subset of singleton 0, and I call this as expression number 2. And now if I compare 1 and 2, so by 1 and 2 we have the equality. By 1 and 2, intersection of all these fk's is nothing but singleton 0. Clear? So this was the first example. Now let's look at the second example. So the second problem says, let R be the universal set and N be the index set. And for each natural number N, a open interval is defined named by Jn, and it is defined to be the open interval 0, 1 by n, where the n is varying over the set of natural numbers, which is our indexing set, right? We have to find the intersection of all these Jn's, where n is varying over the set of natural numbers. So let's pick up some values of n here and let's see how the Jn's are appearing. So J1 is the open interval 0, 1. If I put n is equal to 2 there in Jn, that will give me 0, half. And if I put n is equal to 3, that will give me 0, 1 by 3. And you can keep on going this way. Now, if you try to visualize this on the number line. How will it appear? So this is my number line. Supposing the 0 point is here and the point 1 is here. Let's mark the point interval J1. So J1 is open interval 0, 1. So that will be somewhere here. J1 is here. Let's look at J2, that is 0 comma half. So half is the midpoint of 0 and 1. So it will be here more or less. And this is the interval J1, J2. If you see now, J2 has become half of J1, right? So J2 is a subset of J1, you can see. Then you can mark J3 in a similar way. So let's say 1 by 3 point is here, and 0 comma 1 by 3 is set J3. Then again 1 by 4 will be somewhere here. So 0 comma 1 by 4 will be J4. So as the value of n is increasing, the intervals are shrinking towards 0. Right? Can you see this? As the value of n is increasing, the intervals, that is jn's, they are shrinking towards 0. They are becoming smaller and smaller and smaller in length. So after some time, you'll have 1 by 5 here, 1 by 6, 1 by 7, 1 by 8, and this will keep on going. Right? And what we have to do? We have to find the intersection of all the jn's, where n is varying over the set of natural numbers. So can any point come in this intersection of all the jn's? If a point is coming in intersection of all the jn's, then it has to be present in all the jn's. So let's say it is here, if possible, right? So supposing this is the point which is there in intersection of all the jn's, then even after this point which I've marked in red, even before this, I will have natural numbers such that 0 comma 1 by that natural number will be coming definitely here. So if you take any x here, which I have marked in red, if you pick up any real number x here, then by Archimedean property, I can find a natural number n such that 1 upon n is less than x. And then when I look at 0 comma 1 by n, this x is bigger than 1 by n, so it cannot come in this set. So x will not come in this set, and this is nothing but jn. So our Archimedean property is going to give us this n. Okay, so this existence of n is by Archimedean property. So you can observe that you cannot have any point in the intersection of all the jn's, and hence intersection of all the jn's is a empty set, and that is what we are going to claim. All right, so my claim is intersection of all the jn's is a empty set. So we need to prove that a set is empty. One way to do that is you assume that there is a point in that. Okay, so let if possible x belongs to intersection of all the jn's, where n is coming from the set of natural numbers. So x is there in Jn for each natural number n, because it is there in intersection of all the jn's, right? So for all n in n, x will belong to Jn. But what is Jn? That is 0 comma 1 by n. So this implies x belongs to the open interval 0 comma 1 by n for every natural number n, and a point x is coming in an open interval. This means it must be lying between 0 and 1 by n for each natural number n, right? Now what does this mean? This means x is less than 1 by n for every natural number now, and x is positive. Now since x is positive, by Archimedean property, I can find a natural number m such that 1 upon m is less than x, right? So no matter what positive real number x I pick up, I can always produce a natural number m such that 1 by m will be less than x, correct? So this x is bigger than 1 upon m now, and this 1 upon m being positive, we have 0 is less than 1 upon m, and that is less than x. That means x will not come in the open interval 0 comma 1 by m because it is bigger than 1 by m. So this implies x is not there in the open interval 0 comma 1 by m, and this open interval by the definition of Jn is nothing but Jm, right? So this implies x is not there in Jm. So we have found a natural number m such that x is not there in Jm, but that's a contradiction because x was there in Jn for all natural numbers n. So this is a contradiction. Now why we are getting this contradiction? Because we assumed that this intersection is a non-empty set, right? And therefore intersection of all the j's when you take, that is going to be a empty set where the n is varying over the set of natural numbers. All right, so for all natural numbers n, this intersection what we wanted is nothing but a empty set. So that finishes example number 2. So let's move on to the third example. This example says express the singleton set singleton 0 is intersection of j's where our indexing set is a set of natural numbers where each jn is an open interval. So what I have to do is I have to find open intervals jn such that singleton 0 is nothing but intersection of all these jns, and these jns are open intervals, and the indexing set here is the set of natural numbers, and the universal set is the set of real numbers, right? So if I plot 0 here, then I want open intervals whose intersection will give me 0. So I'm looking out for intervals which are shrinking towards 0 as n becomes bigger and bigger. So if I define my set Jn to be this open interval minus 1 by n comma 1 by n for each natural number n. So then how will this look? When n is equal to 1, I will have minus 1 comma 1. When n is equal to 2, I'll have minus half comma half. Right? So when n is equal to 3, I'll have minus 1 by 3 and 1 by 3. And if you see, these intervals are shrinking towards 0. And 0 will be the only point in that intersection by our intuition. So we have to prove this. Okay. So our claim is zero is equal to intersection of all the j's. I've already mentioned it, so I don't have to write it again. So by the definition of jn, 0 is there in each jn because 0 always lies between minus 1 by n and 1 by n, because this is a negative and this is a positive number for each n. So this implies 0 is there in Jn for all the natural numbers n, correct? That means 0 is there in all the Jn's, so 0 will be there in intersection of all the Jn's, for each n, and this implies the singleton set 0 is a subset of intersection of all these jns where n is varying over the set of natural numbers. So we showed that the singleton set 0 is a subset of intersection of all the jns. Now to show the other side, you start with a point in intersection of all the jns. Suppose x is there in intersection of all the jns, right? So that means x is there in Jn for all natural numbers in, right? This means Jn is minus 1 by n comma 1 by n. So x belongs to this open interval for each natural number n, correct? If it is there in this interval, it should lie between minus 1 by n and 1 by n for all natural numbers n, right? Then only the point x will come in this open interval. And by one of the properties that we discussed in under absolute values, that says minus a is less than x is less than a if and only if mod x is less than a. So if you take a as 1 by n and x is if you keep x as it is, then by this property mod x will be less than 1 by n for all natural numbers n, right? So I have mod x which is a non-negative number, and it is less than 1 by n for every natural number n. So the only possibility for mod x is that it is equal to 0. And if mod x is equal to 0, the number x itself is 0. That means if you start with any real number x in the intersection of all the jns, that has to be equal to 0. Clear? So this proves that, I'll put it down here, intersection of all the jns where n is varying over the set of natural numbers is a subset of singleton 0. I'll name this as 2. And now if you compare 1 and 2, we have actually shown that intersection of all these jns is nothing but singleton set 0. So we have expressed 0 as intersection of open intervals Jn defined by minus 1 by n comma 1 by n for each natural number n. Alright. So this was the intersection of family of sets. And here are some examples for y'all. Y'all can go through these exercises and try to solve these. Okay. These are my references. Thank you.